Every year, thousands of earthquakes ripple across our planet, from imperceptible tremors to catastrophic events. Some of these seismic shifts possess the raw power to reshape entire landscapes in mere moments. They remind us of the dynamic, ever-changing nature of our world. For centuries, understanding these powerful forces has been a monumental challenge. But what if we could gain a new perspective? Can we truly observe these immense seismic forces from the vantage point of space? The answer is a resounding yes. Orbiting satellites are now revolutionizing our understanding of earthquakes and the subtle yet powerful movements of Earth's tectonic plates. They offer an unprecedented view of our planet's restless heart. Our planet's outermost layer, the lithosphere, is not a single solid shell. Instead, it is fractured into massive, irregularly shaped pieces known as tectonic plates. These colossal plates are in a constant, slow-motion dance, moving just a few centimeters each year. This slow, relentless motion is the primary driver of seismic activity. Energy steadily accumulates at the boundaries where these plates meet, whether they are colliding, pulling apart, or sliding past one another. When the accumulated stress exceeds the rock's strength, it releases suddenly, causing an earthquake. Historically, studying these movements relied on indirect geological observations and ground-based instruments. However, the advent of orbiting satellites has transformed this field, allowing for direct, precise observation of Earth's surface deformation from above. A new era in earthquake science began in the 1990s with the launch of pioneering radar satellites, such as the European Space Agency's ERS-1 and ERS-2. These missions marked a significant leap forward in our ability to monitor Earth's surface. They introduced a revolutionary technique that would change how we perceive ground motion. This key technique is known as interferometric synthetic aperture radar, or INSAR. INSAR uses radar signals to measure changes in land surface elevation with extraordinary precision. It has become an indispensable tool for geoscientists worldwide. The true power of INSAR lies in its incredible sensitivity. This technology can detect ground motion as minute as 1 centimeter, even across vast areas. This capability allows scientists to observe subtle deformations that would be impossible to measure from the ground alone. The European Space Agency's ERS-1 and ERS-2 were truly pioneering missions, establishing the foundational principles and capabilities of INSAR. They demonstrated the immense potential of space-based radar for Earth observation. These early missions paved the way for future advancements. Building on this success, ESA's ENVISAT satellite further enhanced global coverage and resolution. It provided a more comprehensive view of Earth's surface, allowing for more detailed studies of tectonic activity and other geophysical phenomena. ENVISAT significantly expanded our observational capabilities. Today, the Sentinel-1A and 1B satellites, also from ESA, provide continuous, near real-time radar data. These missions are part of the Copernicus program, offering an unprecedented stream of information crucial for monitoring ground deformation globally. They ensure ongoing, consistent observations. Beyond Europe, the Japan Aerospace Exploration Agency, JAXA, contributed with ALOS-1 and ALOS-2. These satellites utilize L-band radar, which is particularly effective for penetrating vegetation. This allows for accurate measurements even in densely forested regions, expanding the scope of INSAR applications. Looking to the future, the NASA ISRO Synthetic Aperture Radar, or NISAR mission, promises to deliver comprehensive deformation mapping on a global scale. This joint venture will provide unprecedented detail and frequency of observations, further advancing our understanding of Earth's dynamic processes. Collectively, these advanced satellites function as a global seismograph. They continuously monitor the subtle shifts and deformations of Earth's crust, providing a comprehensive worldwide network for observing our planet's tectonic pulse. INSAR operates on a remarkably clever principle. It works by comparing radar waves emitted from a satellite during 2 separate passes over the same area. The satellite sends out radar pulses and records the time it takes for them to bounce back. If the ground has moved between the 2 satellite passes, even by a tiny amount, it causes a detectable phase difference in the returned radar waves. This phase shift is the key to measuring the precise displacement of the Earth's surface. It reveals the subtle changes occurring below. Scientists then process this data to create what are called interferograms. These are intricate images where color patterns represent changes in elevation or horizontal displacement. Each color fringe on an interferogram corresponds to a specific amount of ground movement. This powerful technique enables detailed 3D mapping of crustal deformation. It allows scientists to precisely identify the extent and direction of fault slip during and after earthquakes. A prime example is the 2016 Kaikoura earthquake in New Zealand, where INSAR clearly mapped complex fault ruptures. While INSAR provides a broad, detailed view of surface deformation, Global Positioning System, or GPS, offers complementary data. Thousands of ground-based GPS stations continuously record their precise positions, providing invaluable ground truth data. These stations offer continuous, highly accurate measurements. The true power emerges from the synergy of these two technologies. Combining the wide area coverage of INSAR radar images with the continuous, precise point measurements from GPS data allows scientists to determine real-time crustal motion with unparalleled accuracy. This integration creates a more complete picture. Furthermore, the global positioning landscape has expanded beyond just GPS. Other global navigation satellite systems, or GNSS, such as Russia's GLONASS, Europe's Galileo, and China's Beidou, now contribute to this vast network. These systems collectively enhance the density and accuracy of global positioning data. Satellites have opened a new window into the subtle, ongoing movements of Earth's crust. They enable us to observe slow surface uplift and subsidence, revealing areas where magma is accumulating or groundwater is being depleted. These observations provide critical insights into subsurface processes. We can also detect fault creep, where faults move slowly and continuously without generating large earthquakes. This silent motion is often invisible to traditional seismometers. Satellites reveal these gradual shifts, helping us understand how stress is released over time. Beyond these, satellites detect periodic deformation linked to geothermal activity, such as the inflation and deflation of volcanic systems. They also monitor post-seismic relaxation, the slow adjustment of the crust after a major earthquake. These observations provide crucial data for understanding Earth's dynamic response. These detailed observations are refining our understanding of fundamental geological theories. They are helping to improve the elastic rebound theory, which explains how stress builds and releases along faults. Furthermore, they enhance models of stress transfer between adjacent fault segments, improving earthquake hazard assessments. What began as a research tool is rapidly evolving into a critical instrument for public safety and disaster management. The ability to quickly map ground deformation after an earthquake has profound implications for emergency response. Satellites are becoming indispensable. NASA's Advanced Rapid Imaging and Analysis, or ARIA, project exemplifies this transformation. ARIA automatically processes radar data post-earthquake, generating rapid displacement maps within hours. These maps are crucial for identifying damaged areas and directing aid. The future promises even greater capabilities. Upcoming satellite constellations are designed to provide near real-time updates of ground motion. This will transform raw data into actionable information, enabling faster, more effective early response systems for communities affected by seismic events. The next decade is poised to bring unprecedented detail and frequency to planetary mapping. New missions and advanced processing techniques will allow us to monitor Earth's surface with extraordinary precision, revealing even the most subtle geological changes. This will revolutionize our understanding. Perhaps the most exciting prospect is the potential for detecting stress accumulation before earthquakes occur. By continuously monitoring minute changes in ground deformation, scientists hope to identify precursors to seismic events. This could transform earthquakes from unpredictable disasters into measurable processes. This future vision holds the promise of enhanced preparedness and mitigation strategies. While predicting the exact timing of earthquakes remains a formidable challenge, space-based observations are bringing us closer to understanding the complex mechanics of our restless planet.